Okay, well, thanks for the smooth transition into this venue, and really excited to pass it over to Matthew very, very shortly. Before we do, I've got a couple of housekeeping notes. It's a bit late now, but if you needed it, the bathrooms were out near the escalator. If there's an emergency, and we are yet to have one here yet, but if there is one, the emergency exits are here and here. So please exit via the exits and make your way down the stairs to outside. And as I said, afterwards we'll have cake available. So I'm just going to, before I pass over to Matthew, just say a couple of words about the Prime Minister's Prize for Science. And Pascal's done a wonderful introduction to Matthew and his career. And Matthew won the Prime Minister's Prize for Science for the discovery of FRBs, which he and his colleagues made in 2007, I want to say. So the discovery of FRBs has actually led to a new branch of astrophysics, and it's got over 1,100 papers published so far. Matthew himself has over 40, maybe even more now, papers on this topic, including more than 20 Nature and Science papers. And so that really demonstrates the enormity of that discovery, which was, as you'll see from this talk, a chance discovery. So without further ado, I'd like to pass over to Matthew and look forward to hearing your lecture. Thank you so much.
Thanks very much. It's fun to be able to talk about astronomy, which is both my hobby as well as my career. One of the stories that I was fascinated by as a very young man was the story of the discovery of pulsars by a woman called Jocelyn Bell. And we're going to touch on that as part of the talk. But it was a serendipitous discovery, like fast radio bursts. And I remember walking into the library at the University of Adelaide and pulling out a book called Pulsars. I didn't realize at the time, but the author of the book was going to be my future PhD advisor, and his co-author was going to win the Nobel Prize in 1993. I read that book and I couldn't really understand it. It was too high level. But there was another book called Black Holes, White Dwarfs and Neutron Stars, and that was a public sort of outreach event. And this coincided with the time that Carl Sagan had the wonderful TV series called Cosmos, which also was an outreach TV series that I absolutely loved and cherished. And I changed my degree from electrical engineering to astrophysics. And Swinburne's Unlimited has intervened. And I've been fortunate to have a career in astrophysics ever since. And I even got to meet the woman who discovered pulsars, which was very special for me. So we're going to learn about the role of serendipity in scientific discovery, which for me, very fortunately, has led to these wonderful accolades. So serendipity was actually a word that was only invented in the 1700s by Horace Walpole, who himself was the son of a prime minister. And there was a book, The Three Princes of Serendip. Serendip was another name for the modern Sri Lanka. And these three princes have all these wonderful adventures with these fantastic coincidences, but they're also a little bit like Sherlock Holmes. And they make these amazing deductions when they come across a camel and realize it must have been carrying a pregnant woman and that it was lame, and make these amazing deductions. And so this word serendipity came about, which means the occurrence and development of events by chance in a happy or beneficial way. And that's certainly been influential on my career, but also on other great discoveries. So Martin Harwitt made a list of all of the discoveries in astronomy back in 1983. And he did this for a book he was writing. And there's things like the stars, planets, novae, comets, and indeed the Magellanic Clouds, which are the nearest galaxies to our own that can be seen by the human eye. And these have been known about since antiquity. Since then, we've developed technology that's enabled us to study the heavens and created things like, or discovered things like the moons of other planets, rings, comets, exploded stars, balls of stars called globular clusters. But it's really the acceleration of scientific discovery really came in the post World War I era. And part of this was the discovery of the radio sky, the sky at other wavelengths. And this led to these wonderful discoveries that I'm going to touch on in yellow here and end up with fast radio bursts. And one of the things that Martin wondered was how many things remain to be discovered. So how often do we get a new class of object in astrophysics? And have we discovered everything already? Luckily, he wrote this in 1983, 24 years before we discovered fast radio bursts. But he pointed out that most things discovered by a new technology occur in the first 5 years of that instrument being born. Like the mobile phone. So Galileo was the first person we know of to take a telescope and point it at the heavens. And it was been known since antiquity that the planets move across the night sky and the stars are fixed. And he used it to point it at Jupiter. And he noticed that there were 4 companion stars to Jupiter, which he sketched in his notebook. And then the next night, he saw that those stars next to Jupiter had moved. And he deduced that they must be moons. And he thought, if Jupiter has moons and the Earth has a moon, maybe they're the equivalent things and the sun is something different. And so maybe Copernicus was right. And the sun, the Earth did travel around the sun. He also looked at something else on the left there. That's actually Saturn. That's his sketch of Saturn. If you have a blurry enough telescope, that is in fact what it does look like. So when he looked at Jupiter, he's noticed that there were these companion moons all in a straight line. And keep in mind that there's 24 hours in a day. And when he looked at the next night, so I can speed up time here, so roughly about every 9 seconds, this is how far the moons of Jupiter move. And fortunately for him, the timescales here were such that they moved a significant amount. And so people started studying the moons of Jupiter. It caused Galileo to be placed under house arrest. Unfortunately, nobody's come for me yet. But the, where's my mouse? The study of the moons actually led to a lot of physical breakthroughs in astronomy. If you look at Saturn, if we stop that at the right phase, you could see if you had a very poor telescope, you might indeed see something that looked like the thing on the left with the bright planet along with the moons. The other thing that was able to be done with the Jupiter system was that if Jupiter was moving around the sun and the Earth was moving around the sun and the speed of light was finite, you could actually time the time at which Io, which is the innermost moon, should appear behind the planet. And because the orbital period was known so accurately, if the Earth was moving, you could actually work out the speed of light. And so the German astronomer Romer actually used the time at which Io appeared behind Jupiter to work out the ratio of the Earth's distance to the sun and Jupiter's and deduce the speed of light. He actually got it wrong by about a factor of a third, not bad, given the technology at his disposal. I think he had it at about 200,000 kilometers per second, not 300,000. People used telescopes to look at the sky and they saw these wondrous things. Didn't quite look as good as this when first discovered, but they used to call these patches of sky nebulosity. A nebula is a bunch of gas that's being irradiated or lit up by something. In the case on the left, it's being lit up by a combination of an explosion and a neutron star that is 100,000 times brighter than our sun and is lighting up the nebula. On the right-hand side is the fate of our sun. At the end of our sun's lifetime, the core will collapse and leave behind something called a white dwarf, which is just here. And the outermost layers will be blown away by an object that's initially going to be about 50,000 degrees. But astronomers had only ever used optical means to study the sky until radio waves were both discovered and utilized for radio communication. So Karl Jansky was born in 1905. He studied physics. His father was a professor, and he got his first job at Bell Laboratories, and they were very interested in using radio waves to communicate across the Atlantic. So he built this wonderful contraption. There's a photo of him with his radio telescope. It doesn't look as pretty as the Parkes or Murray-Young telescope, but it had the great feature that you could work out the direction that radio waves were coming from. He discovered that during thunderstorms there was radio emission, but there was also a regular daily static. And at first he thought it might be due to the sun. The sun was actually very quiet at the time because we were in what's called solar minimum. The sun has an 11-year activity cycle. It gives off radio waves at peak, but not so much at the lower peak. And he realized that the gap between this emission that was appearing every day was 23 hours and 56 minutes. And that's actually the rotation speed of the Earth with respect to the stars. Because the Earth goes around the sun once a year, there's 365 and a quarter days, but it actually spins 366 and a quarter days. And that's a signature that something is coming from well beyond the sun. He worked out the emission was coming from the constellation Sagittarius, but it was during the Great Depression. And he published his findings. Astronomers didn't want to know about it because they were set in their ways of optical astronomy. And although this was published in a scientific paper and also in the New York Times on the very front page, mysterious static reported by K.G. Jansky held to differ from cosmic rays. Direction is unchanging. So they appreciated it. It's genius. Karl Jansky actually had a horrible life. He suffered from a heart condition, and I think he used to drink grapefruit juice and eat cabbage, and that was about it because of so many health issues. And the reason he was sent to this site was really for his health, to get him out of the city. He was fortunate to have the unit of radio power named after him. It's called the Jansky. So we talk about things being Janskys or mega Janskys or milli Janskys or even micro Janskys. And it's the amazing unit of 10 to the minus 26. That's a 0 with 25 zeros and a 1 watts per square meter per hertz. And if you do the calculation, the total amount of energy that's hit the Parkes radio telescope over the last 50 years is about the same as the kinetic energy of a raindrop. So radio waves, although they reveal a lot about the universe, they're actually very weak and very efficient at being transmitted. So the professional astronomers weren't very interested in Jansky's discovery, but a guy called Grote Reber was. He was a very strange man who had a lot of idiosyncrasies, one of which was that he had $4,000 back in the 1940s, and he built his own radio telescope to study the sky. And he kept looking at the sky, trying to detect Jansky's radio emission. He read papers about where the emission should peak, but it turns out all the theorists were wrong, and the peak transmission frequency was actually much lower than he thought it would be. But he built this contraption in his backyard, and on the left here is the data that he used to record. We used to use not computers, but pen chart recorders. They had an ink well, and you would fill the pen with ink, and then you would run paper underneath it at a constant rate. And every time the signal went up, the pen would go in one direction and then it would go back down. And these are actually part of his original recordings of the discovery of radio emission from our galaxy. And all of the little spikes are people starting their car engines nearby. So a spark plug would give off radio emission. So this is Grote's map. He carefully sketched it out after working for some years and published it. And this was very interesting because it showed that in the direction of the center of our galaxy, the emission peaked, but it followed the sky. This is what the modern radio sky looks like with the Meerkat radio telescope in South Africa. Swinburne built some of the instrumentation for this telescope. And if you compare that to poor old Grote's map, it has a little bit more information. And I'm not sure if I have a pointer or not. No. Oh, well, I'll use my mouse. So this is a radio image made with a $400 million telescope. And that little thing there near my mouse is actually a supermassive black hole way behind our galaxy, squirting out jets of material. So it's quite remarkable how the technology has evolved. And right in the middle of that emission is a supermassive black hole about 4 million times the weight of our sun. And then these shell-like things are exploded stars that are very bright in the radio, but quite faint in the optical. So if you look at the sky in different wavelengths, you actually find out lots of new information. And it took the astronomy community a long time to realize that there might be valuable astrophysics in radio wavelengths. By some rare coincidence, I was riding my bike around Tasmania in 1983, wearing a no dam sticker. Some of the older people here might know what that means. The last river in Tasmania was about to be dammed to produce hydroelectricity, which these days we would be applauding. But my colleagues and I went down and rode our bikes around Tasmania, and we bumped into this old guy in a national park. And he was sitting there explaining to his friends how the Big Bang Theory was wrong. And it was out now. And in fact, what happened was as light traveled through the universe, it got tired and the wavelength increased. And it wasn't because the universe was expanding at all. And they were sort of fascinated. And we whispered to each other, is the Big Bang Theory out? I don't think so. But I didn't realize that this was actually Grote Reber. So he had relocated to Tasmania. And the reason he had relocated to Tasmania is there's a hole in the atmospheric ozone layer. That means low radio frequency waves can get through the atmosphere. And he was of the opinion we should all be doing our radio astronomy at that frequency. So he built his own square kilometre array out of poles and wires. And he was a very kind of odd fellow. He invented the electric car. He built an electric car. He had a house that was solar powered. It had a cocoon of glass around it. It used to trap heat. And he didn't used to pay for stamps. He would wait for somebody to send him a letter, and then he would pretend that he didn't live there anymore. And he would say, return to sender. And he would stick his letter in the envelope and send it back. So he was quite a character. And I met him again at the opening of the Australia telescope in 1988. So there was an object discovered by radio astronomers called quasars. Quasars were radio sources that, unlike most of the radio sources in the sky, used to vary a lot from day to day. And the only way you can vary between days is if your dimension is less than a light day. And a light day is only about 173 times the distance between the Earth and the sun. And so they knew that whatever they were looking at, it used to change its intensity in a 24-hour period, must be quite small by astronomical standards. But every time they kind of localized one, there was nothing particular there. The Cambridge astronomers produced a catalogue of these things. 3C48 actually had a blue star where the quasar was, and it had what they called weird spectral lines, and it was obviously a star in our galaxy. But then 3C273 is a very bright quasar. It was actually going to be eclipsed by the moon for the first time in 30 years on 5 occasions. And the astronomers at the Parkes Radio Telescope, or Murray-Young, realized that they could use those 5 eclipses to draw 5 lines, arced lines on the sky and localize this source very accurately. So a guy called Cyril Hazard, pictured on the left there, made these lovely chart recorded images of the intensity of the quasar as it went behind the sun. And he used that to get the position. He didn't email it, but he somehow transmitted it to an astronomer called Martin Schmidt at Caltech, who had access to a 200-inch telescope. That's the Parkes telescope in the middle there with John Sarkisian, who helps us with our observations to this day. And the problem they had with these observations was that you could pre-calculate when they were going to happen to a fairly high degree of accuracy. And the Parkes telescope can only tip over 60 degrees, a little bit further, and it hits the ground. And they realized that it had to go to like 60.5 degrees. So they actually cut off the safety ladders and things and ground down bits of the telescope so it could go the extra half a degree and they could make their observation. So they gave the position to Schmidt. He went to a telescope and took a spectrum, and atoms in stars give off very characteristic lines. And he looked at the spectrum and he couldn't recognize any of the emission. So the top thing is his spectrum of the quasar. The bottom thing is a reference spectrum that just has little sodium lines and hydrogen and oxygen. And you're supposed to line them up to work out if there's any redshift or not. And Schmidt claims that he held up the spectrum to the light and he blocked one of the lines with his thumb. And because of that, he could only see the hydrogen lines, and he recognized that they were regularly spaced in the same way they are at the rest frequency. And there was actually a redshifted source that he was looking at that was traveling at, I think, 16% of the speed of light, which was just completely mind-blowing. And so they had a new object, which was a long way away, many megaparsecs. And he wrote a Nature paper on this, announcing that there was an incredibly tiny object that was ridiculously bright, and he became quite famous. And the paper was actually published on the 16th of March, 1963, which was the same day I was born. So I didn't realize it, but I was destined to be a radio astronomer of some sort. But I haven't spent a lot of time looking at quasars. Maybe I should have. So that's me in Alice Springs. So quasars are both super dense objects. They're very, very bright, and they were completely unpredicted by astronomers. So this was an example of a serendipitous discovery. We now believe that they are powered by supermassive black holes, somewhere between 1 million and 1 billion times the mass of the sun, and that the reason they're shining so much is that they're accreting matter at near the speed of light in a sort of dusty torus that powers both the bright optical emission you can see with the Space Telescope there, but also the radio jets, which extend literally millions of light years away. So there's a black hole at the center of this galaxy. It's accreting the mass from a dusty disk of material. As it approaches the black hole, it goes at nearly the speed of light, and the magnetic field in the accretion disk actually acts as a particle accelerator and squirts out these jets that travel for millions of light years, which is kind of amazing. The next discovery I want to talk about is the discovery of the Big Bang. So Penzias and Wilson worked at this amazing company, Bell Labs, that used to fund, pure science because they saw its value. And their aim was to build the most sensitive radio telescope ever conceived. And so they cooled the receivers with advanced technology. They built this big horn that could be pointed at various parts of the sky. And they had this annoying static that was preventing them getting to their theoretical limit of sensitivity for their telescope. And it didn't matter where they pointed their telescope, this hiss remained. And they thought that accounted for everything. They discovered that the radio horn, as it's called, had filled with pigeon poo. And they thought that maybe, although radio waves bounce off metal structures, they don't necessarily bounce off pigeon poo without gaining extra temperature. And so they cleaned all of the pigeon poo out, and yet it didn't matter. There was still this annoying hiss. They were only working some 30 kilometers away from MIT, where there was another group of astronomers trying to detect the background hiss from the Big Bang. And they beat them to it. And nowadays, if you look at the radio sky, there's a spectrum of energy which has a very characteristic shape, which is exactly what you get from something called a black body. That's basically hot gas. It has no characteristic lines. And the reason this occurs is because when the universe was quite young, the electrons and protons recombined at a temperature of about 3000 degrees Kelvin. And that was at a time when the redshift was about 1100. So if you do 3000 divided by 1100, you get this 2.7 Kelvin background temperature. And it had actually been known that this radiation existed, but it was never really pursued by the observation of carbon and nitrogen that has what's called a hyperfine transition. And so these guys ended up winning the Nobel Prize in 1978 for their discovery, because they'd shown that there was this omnipresent galactic hiss due to the afterglow of the Big Bang. In 1967, there was another serendipitous discovery. We're in the height of the Cold War. The Sputnik had been launched, and the Soviets and the US were in a race to develop the ultimate atomic bombs. And they had a treaty that said that, well, we won't do any nuclear tests without informing each other. But the Americans didn't trust the Soviets. And so they built a constellation of satellites that have a gamma ray burst detector on them. So whenever you blow up a nuclear warhead, and I don't do it too often, there's actually about a microsecond wide burst of gamma rays followed by a long tail. And it's quite easy to build a detector that can detect these things. So the Americans had these constellation of gamma ray telescopes floating around above the heavens. And they were shocked that instead of on the Earth, there was a nuclear explosion gamma ray burst signature behind them. The Soviets doing nuclear tests way away from the Earth? Well, no, it was actually what's called a naturally occurring burst of gamma rays called a gamma ray burst. They discovered 15. They didn't tell the astronomers until about 1973. And my first job at NASA was actually to work on the mission to look at gamma rays from the sky. And this was the distribution of gamma rays observed by the instrument BATSI. And you might notice it's very uniform. And that's because the universe on large scales is very uniform. And the gamma ray bursts were ultimately shown to be from a combination of supernovae, neutron stars that merged, and these things called magnetars. And one of our collaborators here at Swinburne, Sri Kulkarni, actually won the Shaw Prize the year after me, which was good because I could say to him, they let anybody win these things. But it was very nice to have our colleague also win the Shaw Prize. So let's get on to Jocelyn Bell and her discovery. So back in the mid-1960s, a bright Irish woman called Jocelyn Bell enrolled to do her PhD, and her supervisor was the master of studying twinkling radio sources. And we call that scintillation. And one of my colleagues, Daniel Reardon, did his PhD on it and is a postdoc here now. But quasars are so small that they twinkle. There's an old saying that stars twinkle, but planets don't. That's because planets are a finite size. So the quasars were so far away and so compact, they used to twinkle in what was called the interplanetary medium. And Jocelyn's job was to find more quasars. They were quite fashionable. She was working on a PhD from about 1964 to 1967. The quasars had been discovered in 1963. And so they built this array of stakes in the ground and wires and amplifiers. And they used to study the night sky. And it was her job to get literally kilometers of chart recorders and look through at any radio source that might be changing rapidly. And so she did that night after night. And she obviously had a good eye for detail, because somehow she managed to identify that thing called CP 1919 was actually the signal from a neutron star that was rotating with a beam of radio emission every 1.33 seconds, and that it was different than that thing on the right labeled interference, which was probably somebody starting their car or some other form of radio interference. And so if you look at this bottom trace here, there's actually, to the trained eye, a series of pulses, and the y-axis is inverted here. So we get more emission as the trace goes down. And if you look carefully, they're very regularly spaced, and that corresponded to 1.33 seconds of time. And so she had actually used her telescope to discover these things. And she actually spotted that what she called a bit of scruff had moved in time by 23 hours and 56 minutes, which was a signature that it was coming from the distant stars, not from the Earth. And kind of sadly, about 7 years later, her PhD advisor was awarded the Nobel Prize for Physics. And I think many of us thought they should have shared it. Although he obviously didn't decide who won the prize. So neutron stars live in these, or they're born in the explosions of stars. And if you want to study faint radio sources, you want to use the biggest telescopes possible. There used to be a telescope called the Arecibo Observatory, which was a 305-meter dish embedded in the ground. And neutron stars were often discovered with just the very largest radio telescopes. So our current model for a neutron star is this, that it's the core of a star that's become subject to such high pressure that the electrons and protons have been combined together to form neutrons, and they collapse from something about the size of the Earth to something that's only about 20 kilometers across. And they spin. The slowest one is every sort of few tens of seconds, but the fastest one spins 700 times a second. They have these amazing magnetic fields of 10 to the 8, 10 to the 14 Gauss. A fridge magnet's about 100 Gauss, so these things are, a trillion times more magnetic. And when you weigh them, they tend to be between about 1.3 and 2 times the mass of our sun, although Daniel's doing his best to try and beat that record. The density is kind of incredible. A cubic centimeter of a neutron star is 1 billion tons. And there's over 3,500 known. Most of the ones we know about live in our galaxy. And we work out how far away they are by how the radio waves hit our telescope. So if I'm a radio wave, I'm traveling through the universe. If I'm in a vacuum, I just travel at the same speed no matter what my radio frequency. But if I come across an electron, I'm a changing electric and magnetic field, and I don't like seeing another electric field, so it actually slows me down. And the amount I slow down depends on the radio frequency involved. And so if you look at a neutron star halfway across our galaxy, you get this nice sweep where the high radio frequencies arrive first and the low radio frequencies later. And a typical delay is a few hundred milliseconds. So armed with this knowledge, we can get a map of where all the neutron stars are in our galaxy. And these are all the ones we've discovered. There's about 500 have been discovered here at Swinburne using supercomputers, so generously provided by usually Swinburne, but most recently the Victorian state government. They're not all bad, although I'm told not to make any political statements. It's a bit late. And you can see that the distribution of pulsars follows stars in our galaxy. The stars in our galaxy are part of a big pancake. And then if you look really carefully, you can see there's a little cluster of pulsars down here and another one here. They're pulsars in our nearest neighbor galaxy called the Small and Large Magellanic Cloud. They're about 10% and 5% of the mass of our Milky Way. So our telescopes can see pulsars that far away, but until incredibly recently, nobody had ever seen a pulsar any further than that. So we stopped using pen charts to discover pulsars and started using computers. And the first person to use a computer was Joe Taylor. And he and his student, Russell Hulse, actually found a neutron star going around another one. And this was such an exciting object that you could use it to test theories of gravity. And they showed, after many years of patient monitoring, that these two neutron stars have an orbit that shrinks by 3.1 millimeters per orbit. And that's due to the emission of gravitational waves. And so because of this discovery, they not only both won the Nobel Prize in 1993, Joe Taylor managed to mark my PhD thesis as well as writing that book that I'd read as a student, and actually modeled a lot of what we do in the Center for Astrophysics and Supercomputing after Taylor's group. When we were students, my wife and I visited him in 1988. He drove out to the train station, picked us up. We stayed in his house. And I was a bit surprised that he threw a party for us. We met all of his students. And I thought it was a wonderful way to run a group. And so I tried to incorporate that into the culture behind the Center for Astrophysics and Supercomputing. And strangely, after a couple of days, he said, "Oh, I'm going to Arecibo to do some observing. You and Marion can have the house," which was kind of fun. So it was discovered very shortly after neutron stars were first found that occasionally they would give off a giant pulse of radio emission. Normally pulsars just give off regular pulses, but if you're young and energetic enough, you occasionally give off a giant pulse. And so one of our colleagues, Maura McLaughlin, and her PhD advisor had the idea of looking at the nearest galaxy with this giant telescope to see if there were any giant pulses being emitted. And if you did the calculations of the brightest giant pulse emitter in our galaxy, if you put it in this galaxy, you couldn't quite see it, but maybe there was a bigger, brighter one. So they wrote all the software to do this search and found absolutely nothing. But they had the software lying around, and so they applied it to old surveys that had all been processed by computer looking for regular pulses, and they discovered a class of object called the RAT. It stands for Rotating Radio Transient. Not sure I'm a big fan of the name. But these were neutron stars that instead of giving off lots and lots of regular pulses, would just occasionally go bam and give off a lot of radio emission. And here's one of the first ones discovered. This is a Nature paper with about 1,000 citations led by Maura. And you can see that characteristic, what we call dispersion sweep, where the high frequency arrives earlier than the low frequency. And so after this Nature paper, everybody grabbed all the archival data that we had our hands on, and we ran it through our own pipelines. This is Moira's pipeline. And this was how she was discovering her rats. She would take her observation and she would check many different, what we call dispersions. So dispersion measures how many electrons there are between you and the pulsar. And if there was a source, it would rise and fall, and you would detect these exciting new sources. And this is a composite animation. All the neutron stars that are regular pulsars are the little dots, and the big balls are actually where Moira had discovered her rats. So they were all part of our galaxy. But my PhD advisor had actually done a radio survey of the nearest Magellanic Clouds and found a bunch of pulsars. And so if you actually looked at how bright on the y-axis these objects were compared to how long they pulsed for, the rats were a little bit brighter than your average pulsar, but their luminosity seemed to drop off. And whilst it would have been wonderful if they were so bright, we could see them in the distant universe, nobody really thought that was possible. So Moira married my first PhD student, Duncan Lorimer, in a beautiful tale. And they had a baby and they both got jobs at WVU. She's a high psi, by the way, Pascal. He's not a big Trump fan. They got the archival data that Dick Manchester, my advisor, had on this little funny patch here. This is what's called the Small Magellanic Cloud, about 5% of our galaxy. And they got that data, gave it to a summer student, Dan Narkovic, and it was his job to go through the data using Moira software and find rats. And he found nothing except for just one candidate that was fairly convincing, and it had occurred in 2 of the detector beams of what's called the Parkes multi-beam receiver, which I think Virginia used for a PhD. So this was a quite revolutionary thing in radio astronomy. Instead of looking at the whole sky with just one pixel, it actually was like a camera, which was quite revolutionary. And this is where I enter the story. I was observing with Duncan at the Parkes radio telescope, and I said to him, "Have you discovered anything interesting lately, Dunk?" And Dunk said, "Well, I've got this source I don't quite understand." He said, "Have you ever discovered anything with the multi-beam receiver that occurred in 2 beams instead of 1? And I said, "Oh, yes. The exciting millisecond pulsar 1909-3744 appeared in not 2 beams, but 3 beams. So it can happen." And he said, "Oh." And he said, "Well, I've got this pulse. It's got a high dispersion. We're not really sure what to make of it." And I said, "Well, you've come to Swinburne, Centre for Astrophysics and Supercomputing. We've got this wonderful software which can plot what we call the waterfall plot." And they'd been searching for single pulses. This is giant pulses from a neutron star that they used as a bit of a calibrator. And when we looked at their source, it had a remarkable statistical significance. Anybody can see there's lots of circles there indicating a high signal to noise detection. And instead of it being in the galaxy, it was offset from the galaxy, which was a bit of a mystery. So we looked at it with, I think it was Willem van Stratten's software. And the thing on the left is what you see when you look at a normal pulsar in our galaxy. And what was to become known as the Lorimer burst, beam number 13, this was the plot that came up on our screen. And it just looked so perfect that Dunk started laughing. And I started thinking, wow, that's incredible. And then we realized that it also occurred in beam 7, but it didn't occur in beam 6, which was a little bit odd. And then we realized that our software was so clever that if the statistics of the data didn't follow our idea of how the universe should behave, we would delete it. So the brightest pulse actually got zapped by our software. I didn't write that bit. It was Andrew Lyne, my old my first postdoctoral advisor. But he thought there was nothing in the universe that bright that we didn't already know about. So he didn't care. But luckily, because of what's called the side lobes, we did detect this burst of radio waves. It was about 5 milliseconds wide. And as you can see, uniform across the spectrum. And if we worked out where it was quite a bit south of the small cloud. And so we worked out how many electrons there should be between us and the cloud. And it was only about 50 odd units. And so there were another 325 that weren't explained. And I'd never really thought about cosmology because pulsars were all in our galaxy. And we started reading papers, and it was quite an exciting time. And then we realized this thing was 1 billion light years away. And it was like, whoa, this might be something really significant. And the beds at Parkes weren't very good. They had these horrible woolen sheets, and I've got very sensitive skin. And I just couldn't sleep. I thought, maybe this is some amazing discovery that we've made. How can we convince ourselves this is real? And this was the idea that something had happened in a galaxy far, far away. It had traveled for 1 billion years. It had gone just past the small cloud and arrived in the Milky Way. And the emission, although it started off undispersed, as it had traveled through the universe and come across all these electrons, it ended up being very dispersed. And it took about 0.4 of a second to go from the highest radio frequency to the lowest. The observation had happened about 6 years earlier and was just sitting on a magnetic tape waiting to be discovered in my supervisor's office, which was kind of funny. Duncan had actually been my first PhD student. So we had a discovery that my supervisor had initiated. My PhD student had a summer student who detected it. And then I was caught in the middle of it all, being very excited. And so when we plotted it on that graph of how luminous something should be compared to how long it should last, you could see that it was about a factor of 10 to the 12 times brighter than anything anybody had ever found that had the same temporal or timing characteristics. And I remember saying to Dunk, you know, if we play our cards right, this might be a wonderful discovery. The only problem is there's only one. And nobody else has ever seen anything like it. And it means that the luminosity function goes down, and then it actually extends another factor of 12 orders of magnitude. So let's write a Nature paper. So we submitted it to Nature. The editor read it. He gave it to a few people just to look at, not properly referee. He said, we're not going to publish your paper. We don't believe it. Come back when you found some more. So we deleted the Nature submission guidelines and added science and submitted it. And we had amazing referee reports, and it was published. And it became known as the Lorimer burst after the project leader, Duncan Lorimer. And we wrote the abstract, which in retrospect was kind of brave. I won't read the whole thing, but you'll notice the 30 Jansky pulse. So it was named after Jansky. It was less than 5 milliseconds in duration, a few degrees from the Magellanic Cloud. I went back to Parkes and I pointed at it for 90 hours, waiting for it to repeat. And it didn't. And we just have this casual note at the end. Hundreds of similar events could occur every day, and if detected, could be used as cosmological probes. So people were really excited about this event. Everybody wanted to find more. And the question was, you know, how many we were missing. And it turned out the Parkes receiver only looks at it less than 1/50,000th of the sky. So there could have been these things going off everywhere. How many we were missing, that wasn't particularly clear. It must have been something very small. The light travel time gives you an idea of the dimension. And the emission couldn't be too random. It has to be something called coherent, where all the photons are in phase. And so people were kind of very excited. Dunk became famous, which was very nice. A band was formed called the Lorimer Burst, and the title of their album was Dispersion. And we started appearing in other novels and things. I had a student called Sarah Birksplore, another high sci by coincidence, who did a PhD here. And she contacted me when I was on sabbatical at Berkeley and said, "Good news, I found another Lorimer burst." I'm like, yes. And she said, and it's in all 13 beams. And I thought, that doesn't sound right. There should only be in a few. And then she named these things the peritons, because the only way you can appear in 13 beams if you're within what's called the near field of the telescope, i.e. within a few kilometers. And these things weren't. But they did have a sort of dispersion sweep, but were kind of blotchy. And this is what she labeled the peritons of unknown origin. And I started getting all worried because these looked a little bit like a Lorimer burst. So there were some of them kinked and they were never quite as smooth, but they were occurring in all 13 beams of the receiver, which was kind of terrifying. And people started losing faith, including myself. And I even sent Duncan a Lorimer email saying, "Do you think we should retract the paper? Because these things look a bit like peritons." And luckily he said, no, keep the faith. So we did. And then about 5 years later, nobody had found any. We knew that there was something giving off dispersed pulses. Evan Keane, who was a former postdoc here, just before he arrived, published a paper showing that there was a burst that looked a bit like the Lorimer burst. It had reasonable dispersion. Unfortunately, it was right in the plane of our galaxy, and people just said, "Oh, it's just something in our galaxy." So shortly after the Lorimer burst, we planned a series of surveys. Here's the Swinburne team at the Parkes Telescope, Andrew Jameson, Lena, Ramesh, and we were commissioning a new instrument that had many more frequency channels than has been used before, and we're much better at finding dispersed things. But we found probably 500 pulsars with that instrument. And Dan Thornton, who was a student of another student of mine up in Manchester, had the job of searching the sky for Lorimer bursts. And he found 4, and it was magnificent. One of them was incredibly bright. It was 3 times further than the Lorimer burst. It was probably at a time when the universe was less than half of its age. And when these were discovered, past radio bursts became a bona fide field of interest. When you plotted what their dispersion was compared to where they were in the sky, it was clear they weren't coming from our galaxy. And then other telescopes started finding them as well. Arecibo found one called 121102. At Parkes and Molonglo, we also started finding them, including some very bright ones. They had curious fine structures, which showed that they were coming from something reasonably complicated. And eventually we discovered that the microwave oven at Parkes actually gives off fast radio burst emission if you open the door while it's still on the on cycle. And this was deduced by Emily Petrov, who was one of our students here. She discovered that all of these things used to occur at lunchtime. And luckily the Lorimer burst had happened at 5 a.m. when the visitors center was shut. So one of these fast radio bursts was found to be repeating, and our colleague Shami Chatterjee localized it to a little baby galaxy about 3 billion light years away. And so this established that they were firmly cosmological. Now everybody's finding them. One even occurred in our own galaxy and was detected by a little tiny radio telescope only 20 centimeters across. It came from a magnetized neutron star. Our colleague Vicky Caspi led a project in Canada that seems to find one almost every day. And this team at Swinburne's been leaders in using the ASCAP telescope to localize them to exactly where in a galaxy they occur. So Ryan Shannon, Adam Della have been leading that work. And we finally managed to collect all of the fast radio bursts detected and plot how far away the redshift was versus their dispersion measure, and show that there's about 1 electron per cubic meter in the universe and effectively weigh the universe. So one of the most recent Nature papers was a fast radio burst when the universe was only about a third of its current age. And so I just want to finish by musing, well, how lucky are these unplanned discoveries? Should we just be, as scientists, looking everywhere and trying to hope for the best? And many of these discoveries would have been impossible without new technology. In the case of the Lorimer bursts and the Thornton bursts, it was the technology we developed here at Swinburne and deployed at the telescope that enabled us to confirm the Lorimer burst. And the equipment for that Lorimer burst discovery was made by my old boss, Andrew Lyne, who used kind of quite archaic technology, but did make this wonderful discovery. So Louis Pasteur said, in the field of observation, fortune favors the prepared mind. I think that's how I like to think about it, but there's no doubt luck played a role in this. So it's been wonderful to be part of these discoveries. And I want to thank Swinburne again for supporting me in my dreams and trying to emulate Jocelyn Bell, who wrote the reference letter for me for the Prime Minister's Prize. And I think being trained well matters. Dick Manchester was my PhD advisor and the author of that textbook. And if you look at this, I wouldn't say plot, this picture, this is back in 1996. And 3 of the people under his care won the Shaw Prize. And David Helfand on the right helped run Quest University in Canada. Brian Gainsler won the Young Australian of the Year, and many of the other people here are professors at prestigious universities. So I'm very lucky to have both had the support of my family to appear at these glossy events, but also partake in these wonderful discoveries. And I'm just going to give you a shot here of a system we're developing here at Swinburne in the future, which is going to be called Swinburne's Virtual Universe, which will be a room full of LED panels where you'll be able to come and hear us tell other stories about the universe, but be surrounded by 3D graphics. And I'll finish there. If you want to, you can do a quiz about the lecture by scanning this QR code if you're young enough to know what that means.
Fantastic. Thank you so much, Matthew. I think I can say for everyone, it's inspiring to see the achievements, but also understand the history that got you to this point. And surely just serendipity plays a role, but you need to know what you're looking at as well. So, so thank you so much. We do have some time for questions. If anybody in the audience has a question for Matthew.
Tom. You won't wait for the microphone.
Is there as well as 3 emissions of waves from a pulsar? Can there also be 4?
Yes, there can be many patches of emission from pulsars. And I think one of our PhD students recently wrote a paper on 10 or 11 that had come from a single fast radio burst. Pulsars have very complex emission, and something called the magnetars give off lots of little sparks that can give you dozens of pulses of emission. Behind you, Paul.
Thanks so much, Matthew. You mentioned in your talk archival data and, you know, trawling through that archival data and the software, you know, that was used in these discoveries. And so I'm just after like any sort of further elaboration or comment on the importance, like we hear the superlatives about how much data are being produced by telescopes these days, and we don't want to lose any of it. So we're just going to get more and more and more, and this is good, right? Like, because we want to go back and look at this archival data, and yeah. So I guess I'm just interested in any comment on data, like importance of data storage and access and the software services that go along with that?
Yeah, I think that's an interesting point. I think there's elements of generosity around these discoveries. So the data that was used was taken by my PhD advisor, and he made a copy of it and mailed it to Duncan. If he'd been a bit more bloodthirsty or ruthless, he might have decided, I'm not going to share anything with you because maybe there's something I haven't discovered in it. And so I think if people hoard data, it actually prevents discovery. And I think we were very generous that he provided that data at sort of no cost to, admittedly, one of his former kind of grad students. But I think there are fields in which people are absolutely ruthless to each other and they decimate each other's grant applications and are just kind of really nasty. The radio astronomy community is kind of small, and I think that's helped have positive relations between many of the groups. And I feel that there's been a lot of generosity around data sharing. And one of the principles I try and make with anything I build is that anybody can use it.
I think we're going to have to leave the questions there because we're at time, but I don't know, Matthew, if you're happy to answer.
Sparrow had a question. You're welcome to come down and ask it later.
Yeah, maybe we'll do that. So if we could please thank Matthew again and congratulate him again on the PM's Prize for Science. And don't forget to pick up your piece of cake on the way out. So thank you so much for coming today. Thank you.
Excellent.